Now let's study the second topic today, the ray tracing for lenses. So let me first remind you that one thing. So we studied the ray tracing for the mirror. And what is the difference between the mirror and the lens? So when the light interacts with the mirror, the light cannot penetrate through the mirror. They always be reflected. However, for the lens, when the light interacts with a lens, the light could be reflected or refracted. So that is why we want to study the ray tracing for the lens, because the light can actually penetrate through. And in this class, we are only going to focus on the symmetric lenses, which is double concave, which is this one. Both sides is concave or double convex. So let's focus on the convex one. So not a surprise to you, the convex one, they can converge the light to a so-called focal point. Therefore, the image can be formed there. But why the convex lens can converge the light? So let's assume that the convex lens is composed of the prisms. So the upper one is composed by this shape of the prisms. So we just learned the law of the refractions. So what happens is that when the parallel light hit on the first surface or the first side of the triangle here for these prisms, because of the law of the reflection, now the light is entering from the low index of refractions to a high index of reflections. So which means the light will be bended toward to the normal line. Agree? And now after the light was bended toward to the normal line, they will continue move in a straight line and hit the other end of the triangle. So now they are leaving the prisms, which means you are leaving from an environment with high index of refractions to a low index of refractions. So now the light will be bended away from the normal line. So here I already draw the normal line for you for each of the interface. So therefore, for the upper one, no matter where the light is from, as long as they follow the parallel direction there, the light will definitely all be bended downward. So you can try to convince yourself, if you make the triangle upside down, like this, then all the light will be bended now upward. So that's the reason for the doubly convex lens. They can converge the light. So now, not a surprise to you, for a concave lens, they can diverge the light. So you can still once again consider the double concave is made of by the two prisms, but now you can see the shape of the prism is opposite in the previous case. So apparently the upper one there now, they will diverge the light. And the lower one also will be diverge the light. But still, the light can passing through the lens. It is not reflected. So in the previous lectures, when we studied about the ray tracing for the mirrors, we defined the so-called three rays. So similar thing, we should define the concept here. The first is the P ray, which is the same as before. They are the parallel ray to the axis. So this is the P ray. They are parallel to the axis. The second thing is the F ray. It is the ray going toward or passing through the focal point. So for example, this is a parallel. When they're passing through the lens, they will gather and enter into the same point. And this point is a focal point. So this one is a P ray. It is the F ray, not the P ray. Then finally, the M ray. This is a new one for the lens. It is the middle point ray. It is the ray goes through the middle of the lens. In that case, they will not be deflected. So do you remember I mentioned that all the ray, all the light is passing in the same directions of the normal line. They will not be refracted. So that's the reason now you have to define the so-called M ray, the middle point. And here it is based on the thin lens approximations. If it is thick and thicker, then it may not be true. But in this case, you can simply just apply the M ray is always passing through the middle of the lens and will not be refracted. So therefore, you can use the three rays I just introduced you to create or draw where the image was formed. So for sure, we should focus individually for the concave and convex. So now let's try to study the case for the concave, doubly concave lens. So you put an object here, and this is your focal point. So the object is outside the focal point. So first, let's draw the P ray, which is parallel. So they will be diverge, yeah? But this diverge ray, when you trace them backward, they will passing through the focal point. Now, the second ray is the F ray. F ray is the one passing through the focal point. So you will say, why we have the two focal points? Because this is a doubly concave lens, yeah? So you have the focal point on both ends. So apparently the light supposedly after they passing through, they should go in the direction of this one. They will passing through the focal point. However, because the lens in between, they will be refracted. So after that, they will become parallel. So now, if you trace this parallel F ray backward, you will see the dashed line of the P ray and F ray will intersect at one point. And this point actually can be connected to the top of the object and to the center of the lens, which is the M ray. So therefore, you can find out where the image is formed. And if you still remember our conclusion in the previous lectures, if you have a virtual image, it is always upright. So you can see that it is upright. So the image is virtual. Now let's try to study for the convex, doubly convex lens. So we still have the focal point on both ends. So P ray originally is parallel, but now you will be bended, and you will be bended and passing through the focal point. M ray will simply go through the center without being refracted. And now the F ray will passing through the F ray on the other side of the lens, but after refracted, they will be parallel again. So you will see now the 3 points will intersect at one point. So they will form an image. But now, the example I give you here is that the image is downward. So which means it is a real image. But the situation is a little bit more complicated. Because depend on where the object is put, the image form may be real, may be virtual. And the scenario is even more complicated than the mirror one. Because now you have to separate into 2F and F. If you put the object which is outside the 2F, you will form a real image, but this image is smaller than the original size. If you put the object on the 2F, not the F, if you put on the 2F, then you will form an image. Still, it is a real image, but it is exactly the same size of the object. But now, if you move in between the one focal lens and the two focal lens, in between this distance, you will form a real image, but now the size of the image is bigger than the size of the real object. And finally, you will see that if you put the object on the focal point, ideally you will create a two parallel line, which means ideally you are not going to form any image, or you can say the image is infinitely large or big. So you can see now the image was formed bigger and bigger when you approach into the lens, but when you enter the distance between the lens and the focal length, now the image form will be virtual. And this virtual image is bigger than the real size. And for the concave lens, it is much simpler. The image form is always virtual one, and the size is always smaller than original size of that. So as usual, I give you the summary of the result I just mentioned. For the concave lens, it doesn't matter where the object is. The image is always virtual and upright, and the size is always smaller. But for the convex, it is very tricky. It depends on focal point, focal length, and it also depends on two focal lengths or one focal length. But if it is beyond the one focal length, then the image is always real, and the closer you get into, the bigger it will be. But if it is inside the focal length, then the image will become virtual, and now they will become smaller and smaller when they approach into the lens. So I understand that this is not an easy thing to remember, but since our final exam is an open exam also, so I will ask you is that understanding how to use the ray tracing to self-convince yourself this is true. Don't try to remember that. Use the ray tracing approach to convince you that the image form is real, virtual, the size is bigger or smaller. And also, we will have the so-called thin lens equations. So you will find out the thin lens equation is I should say the same as before. So what do you mean? Approach is similar as we use when we derive the mirror equations. We use the similar triangles. So in the diagram A here, these two triangles is similar to each other. So if these two triangles is similar to each other, which means that is H0 divided by the F for the first triangle. This ratio should be the same as a negative HI. HI is negative now, don't forget about it. Negative HI divided by the DI minus F. So these two ratio will be the same. So this is the first equations. Now let's take a look about the figure B. So these two triangle is also similar. So therefore, for the first triangle, the H0 divided by the D0, the ratio of these two values will be the same as negative HI divided by the DI. So the trick is exactly the same as before. Then now you use these two equations, you can derive actually the thin lens equation is the same as before we used for the mirror. And the definition of the magnification is M, which is HI divided by the H0. And the same HI divided by H0 is negative DI divided by D0. So this is the thin lens equations. But once again, the sign is very tricky for the D0, H0, and DI, HI at the focal point, focal length. So if you have the convex lens, then the focal length is positive. If you have a concave lens, it is negative. So this is the same convention as before. And the magnification for the upright image, it is positive because they are both the HI and the H0 is positive. Yeah. So still the same as before, and negative for the invert image. And the image distance DI is positive for real image, and DI is negative for the virtual image. So what do I mean by real image? It is the image on the opposite side of the lens. So you see the critical point now. It is the image form on the opposite side of the lens. If it is an image form on the same side of the lens, then it is a virtual one, so DI is negative. So the same, D0 is positive for the real object and negative for the virtual object, but you can consider it is a light diverge or converge. So now let's have our last conceptual quiz today. So if you have a point P ray here and no image is seen, then where you should put that? And the answer is between F and the lens. And the explanation is because the image form is a virtual one, so they will not be shown on the mirror. So now let me give you examples. So this is a doubly convex image. So you want to produce a real image, and the distance is twice as large, the size of the image is twice as large as the object. So you already know that HI is 2 times H0 already.